So, hello everyone, and welcome to this new course that we are starting from today. So, first of all, uh, I and Akanksha would like to thank you for joining this course, and I'm sure that we will have a great time learning the design and detailing of RCC structures using the ACI codes. So, this is the first time that we are conducting such a course based on American codes for concrete design. So there are a lot of things new that we are also learning uh, in while preparing or while studying the ACI codes, and I'm sure you will also get to learn a lot of new things during this course. So let us begin. And before that, I hope the voice everyone is able to listen to my voice, and also they can see me, and this presentation is also visible. So generally, what we do is that in the live sessions that we conduct, uh, just a minute. Yeah. So in the live session that we conduct, you will be kept on mute, and all the participants uh, will not be able to directly turn on their mics and talk to us. So the only way to communicate will be through chat. So during the session, we will be continuously monitoring the chat. So whatever questions you have, or any comments, or any thing that you would like to add, you can just type it in the chat box, and we are continuously looking at it. So appropriate response will be given. Okay. Right. So let us begin. This is the session one, and I'll just run through a quick uh, a few slides over here. So a few things that I would repeat from the introductory session that we had conducted. Why to learn concrete design we had discussed then also. So why to learn concrete design using ACI codes? Because I mean, you have joined the course, so you want to learn the RCC design using ACI codes. But why do you want to learn it, or why these days, or why it is becoming important? Because world over, you see one of the most up to date design standards are your ACI based standards. By up to date, I mean that they are regularly revised, and whatever research is happening during, let's say, 4 5 6 years, that gets included in the newer revisions of the code. So it is quite up to date, I would say, and a widely used design standard. And not only it is used in America, but also in a lot of countries across the world. uh, they either follow directly the ACI codes, or their country codes are based on them. All right. So large portions of countries in the Gulf region, or even in the Indian subcontinent, countries outside India, or East Asian countries, African countries, they tend to use uh, ACI codes or codes based on them. So many Indian engineers or international engineers also who are doing these projects, uh, nowadays they have this requirement that they should also be aware of, or they should also be able to do the design using the international standards. And that's why we thought that this course should be conducted, so that we can equip the engineers with this international design codes, concrete design code, that is. We have already conducted the AISC steel design course. Okay. So this we have already conducted in the past just now. I'll just clarify one thing because there's a lot of confusion with these terms. So what does ACI stand for? What does ACI stand for? So ACI stands for the American Concrete Institute. I hope you are able to see this whiteboard. Is the whiteboard visible? So ACI stands for the American Concrete Institute. So what does it do? So whatever concrete based codes or whatever RCC design codes are there, those RCC design codes are those RCC design codes will be published by the American Concrete Institute. Okay. So all the RCC codes, code of standards, they will be published by the ACI. Then there is another body called as the AISC. So what is its full form? AISC. So it is American, yes, American Institute for Steel Construction. Okay. So all these steel-based codes, all the structural steel-based codes will be published by the AISC. Is that clear? Then you have got the ASCE also. What does this stand for? So this stands for American Society of Civil Engineers. So American Society of Civil Engineers, their most, I would say, well-recognized code will be the ASC 7 that we would be referring to. So what is ASC 7? This is going to be our loading code. So all sorts of loads when we will calculate whether it is the dead load or the live load or the wind load, earthquake load, temperature loads, blast loads, tsunami loads, snow loads, whatever loads you want to calculate, you will calculate it as per the ASCE 7. The steel design basic parent code for structural steel design is the AISC 360. Okay. And the parent code for RCC design is the ACI 318. So is this clear, the terms? So unlike in the Indian scenario or even in the European standards, for example, uh, in India we have the BIS, okay, Bureau of Indian Standards. So all our codes are named as IS and then whatever the name, or let's say in the European Union these days, it will be EN followed by the code name, or after the British, after the England have quit from the EU, again they are back to their BS, again they are back to their British standard nomenclature, or Canadian is I think CSA, whatever. So what I want to tell you is that these different bodies are there in US. One is this ACI, which will bring the RCC codes. Then there will be AISC, which brings up the steel codes. And then there is this ASCE, which brings up the loading codes. Similarly, there are more bodies. There is this AWS, American Welding Society. So this brings out the codes based on welding and structural connections. Then there is this another body, I think AASH, TO, Ash, American Society for Highway and Transport Officials, something like that, if I remember it correctly. Okay, so all the, just like we have the IRC, Indian Road Congress, which brings out all the design standards based on the or required for the transportation engineering. Similarly, in the US, we have this AASHTO, if I remember it correctly. So this is their body which brings out the transportation and highway related codes. Then there is this ANSI. I'm forgetting its full form, but I think this committee or this society or this organization brings out the cold form design codes. So the cold form design standards are brought out by ANSI, if I remember it. So there will be these different societies or organizations which have the task of bringing out different design standards. So it is not like in India or even in other countries where they have a unified body under whom or under which all the design codes are brought out. US is slightly different in that manner. Is that clear? So ACI, AISC, and ASCE. So many times I've seen people saying ACI for steel codes or AISC for concrete codes. So no, if it's a concrete code, it will be brought out by ACI. If it's a steel code, it will be brought out by AISC. All right. So I hope that clarification will help you. So So this ACI 318 is a comprehensive document that we are going to study during this course, and there are a lot of things that have been covered in this document. So it needs a lot of unpacking. That's what we are going to do. Also, the ductile design detailing that we are going to emphasize on is based in the ACI 318 itself. In the Indian context, let's say we have a different code, IS 13920. Okay. This thing does not happen over, I mean, this is not the case in the ACI standards. So ACI 318 itself contains the ductile design detailing also. Uh, so that we will be looking into. And then as an engineer, if you are learning ACI codes, you should be well versed with softwares like ETABS or SAFE. So that aspect also we are going, based on, of course, the ACI codes. So that aspect also we are going to cover in depth. I hope my voice is still audible. So today is the first day, so I'm just asking. Voice is audible, right? Yeah. And screen is also visible. You can see the what I'm writing. Good. So yes, good. So this is why uh, learning ACI codes becomes important, and because there are no proper avenues available, most of the times the structural engineer is forced to learn on their own on the job, and this becomes a hurdle also because I heard from many of you engineers that they were having this requirement in their organization to do a project, but that project was based on American standards. So they were asked by their management to either learn or then they were not given a chance to work on that project. So because of lack of availability of a credible platform, structural engineers face this issue. So through this course, we are going to address all these challenges that structural engineers have been facing. And we have already taken you through the details earlier also in the introductory session. So these are some of the things that we are going to cover. Okay. So we'll begin today in this session. We'll begin by understanding the structural systems and their load path. And in today's session itself, we will be having a look at the historical development of ACI codes over the past 110 years. Then we will be looking into the different limit states of strength, serviceability, durability, etc. Then discussion on materials, calculation of sectional strength, etc. Then we will move to gravity load calculations as per the ASCE document. Uh, then this analysis requirement discussion will be interesting because we will be looking into the analysis requirements, the linear analysis, the geometric nonlinear analysis, and so on. So this will be interesting things that we will be discussing. Then we will move on to member design. So these are the different members or elements that we are going to cover. Beams, starting with beams, one-way slabs, two-way slabs, flat slabs. We'll be doing flat slabs also in this course. Then columns, structural walls, diaphragms, collectors, cords, etc. Joints, beam column and slab column joints. And then we will also look into the foundations, basics, uh, raft, combined, raft, pile, isolated, etc. We'll also look into the strut and tie analysis approach. which is given there in the ACI 318, and now it has been included in the IS 456 draft also. So recently, just last week, I think many of you might have seen that the IS 456 draft. Uh, so this is a preliminary draft, not for wide usage, not for wide comments, but the internal circulation. So if you might have seen that, they have also included the strut time method as a chapter in the draft of IS 456. So it will also make way in the 456 code now. IS 456 is the Indian standard for concrete design, just like you have ACI 318 for American code for design. So this strut and tie method is there in the American standard since a very long time. It is there, I think, in the chapter number 23 or 24, I guess. So we'll be looking into this. Then we will go to, after these things are done, we shall go to the ductile design and detailing of RCC structures. So chapter 18 onwards, for 4-5 chapters, the ductile design detailing aspects are covered. So we'll be looking into that during the course. So I'm just giving you a quick walkthrough of the items that we are going to cover. We'll be focusing on the IMRF systems. So IMRF system as of now do not find mention in the Indian codes, uh, but they have been a part of the American code for a very long time. And where this IMRF is used is basically in the flat slab systems. So in IMRF, you have a system which is slab without beam system. I don't know if you have seen that slab without beams. So slab without beams means what? Slab without beams will mean our flat slabs. So in the Indian standard, what is there right now? The requirement is if you are having a flat slab system, it has to have structural walls with it. All right. I don't know if you're aware of this or not. How many of you are aware? As per the Indian standard 13920 requirement, if you're having flat slabs, the lateral load carrying element has to be a RCC structural wall or a shear wall. Okay, that is the requirement of the code right now, Indian code. From time to time, I will be referring to Indian codes also because many of the participants are going to be from India. So just to give some context and just to give some reference with the Indian code also, from time to time I will be giving some uh, I'll be giving some references to the Indian standards as well. So as per the Indian standard, the requirement is that if you are having a flat slab system, it has to have RCC structural walls to take the EQ load, earthquake load, tidal load. But in this American system, American standards, there is this intermediate moment resisting frame. So that has a ductility level which is in between the ordinary and the special moment frame. In that intermediate moment frame, there is a system called as slab without beams. So what is slab without beams? So slab without beams is flat slab systems or flat plate systems. So if you are having a flat slab building in zones of medium earthquake risk, you can go for an IMRF system also. So this is a thing that we will be discussing during the ductile design detailing part. And then, of course, we'll be discussing these SMRFs, special moment resisting frame, and the special RCC structural wall systems. So the requirements, the rules, detailing rules, all these things we will be discussing. And then we will finish with two sample projects. One will be a flat slab system, flat slab building, and another will be movement frame. So these are the items that we are going to cover. Now let us understand that any element or any member Which are the design actions it has to resist? Yes, please. Any element or member, whether it is uh, part of a two-story residential structure, or that member is a part of, let's say, 100-story structure, or that member is part of bridge, or that member is part of a retaining wall, wherever, or that is a structural PEB building, or it's a structural steel, I don't know, dome, whatever. So whatever may be your element or whatever it may be your member, what are the major design actions that can be expected? Tell me, which are the major design actions that can be expected on your member? So there will be, as Mr. Jay is saying, there can be compression. Okay, the most basic uh, will be compression. So compression is in sync with the nature also. Why compression action is in sync with nature? Why the action of compression is in sync with nature? Because compression means it is acting in the direction of gravity. So if it is acting in the direction of gravity, it is, I would say, closest to your natural flow of forces, isn't it? So compression is the action that is associated most closely with your natural flow of forces. Uh, Another action that may be there in the member or element can be tension. Both of them, we will call them as axial actions. Why axial? Because they are acting along the longitudinal axis of the member. So compression induces compression in your fibers, or it induces uh, contraction in your fibers along the length. Tension induces elongation in your fibers along the length. Both of them will be called as axial actions. Then there can be bending or flexure, isn't it? Very basic things. Another action that is possible, which is generally associated with flexure, will be shear. Another action that might be possible quite commonly is a twisting along the longitudinal axis of the member, which we call it as the torsion. I hope you are all with me. Okay. Another action can be your bearing. Okay. Is this clear? So bearing means where the load transfer takes place, compressive load transfer takes place usually through the contact area. So if your load transfer is taking place through contact area, we usually call it as the bearing action. So is there any other action that you can think of? Hello. Except for these five, six that I have given, six actions that I have listed out, is there any other action possible? Tell me. Is there any other action possible? Now see, that might be, you might be designing a G+1 structure, or you might be designing a 100-story structure. You might be designing it for earthquake loads, or you might be designing for wind loads, or as I told you, you might be doing a major bridge, or you might be doing a dam. Whatever structure you are doing, is any design action other than this possible? So either these, as Mr. Zoeb is saying, either these or combination of these. Yeah, combination of these is possible. So you might have compression with bending, or you might have tension with bending, or as I told you, you generally have flexure, that is bending and shear together, or you might have compression with bending, shear, and torsion, or there might be bearing and compression and flexure, so on. So there can be combination of these or some of these actions that are acting. So as an engineer, we must understand that whichever element or whichever member we want to design, we must be able to understand that which actions are going to be generated, and then we should understand how to cater to these actions through the design process. Okay. So these are, as I have just listed out, these are going to be your major design actions that we need to be resisted. And then to resist it, what do we come up with? To resist these actions, what do we come up with? So we come up with, to resist these actions, we will come up with an assembly. We come up with an assembly of members, isn't it? We come up with an assembly of members. Is that right? And that assembly of members, we call it as what? That assembly of member, we call it as what generally? So we will usually like to call it as a structural system. So it will be assembly of multiple members connected together to form a structural system. And what is their purpose going to be? So their purpose is going to be to take these, to resist the design actions that are produced by the loads acting on them. You get it? Why we are talking this? Because we just wanted to start our course with a basic discussion on the structural systems. That's why. So, so I just written down what is a structural system, and this line I have taken from the ACI 318, chapter number 4. So in the ACI 318, chapter number 4, they have just written this in one of the clauses. So a structural system is, or sorry, comprises of structural members, and not only structural members, but joints, yeah, and connections, and each has to perform a specific role or function. So you see, joints are also emphasized on what used to happen earlier in our earlier thoughts. See, in RCC, what happens is, because it is monolithically cast, we usually don't talk a lot about the joints, isn't it? Hello. Because RCC elements are cast monolithically, we don't often talk a lot about joints and connections in RCC. In structural steel, we put a lot of emphasis on connections because everything is heterogeneous. Heterogeneous means everything is a separate item and then they are joined together. So in steel elements, connections play a big role. So this is my connection, let's say. This is my beam, this is my column. So in steel or even in precast, connections play an important role because in precast also there are dissimilar heterogeneous items. Heterogeneous, by heterogeneous I mean that they are not monolithic, they are heterogeneous and then be connected through some external entity which is called as a connection. But in RCC, usually, if you see, we don't talk a lot about connections, isn't it? Or joints. Why? Because because of the very fact that the RCC is cast monolithically. It's a union. Okay. But in the American code, if you see, and increasingly in the Indian standard also, there's a lot of emphasis on the joints all as well, joint locations also. Okay. So the beam column joint or the slab column joint, they have a lot of importance, especially under gravity loads or lateral loads. What will you say? In RCC, I'm talking about these joints, the beam column joint or the slab column joint or the column footing joints or the splices that we create in reinforcements. So these have a lot of importance during gravity loads or lateral loads. So in RCC systems, generally they have importance in the lateral load transfer. So during the wind and earthquake events, how the joints are behaving is very important, and that's why a lot of emphasis is placed on joints as well. So a structural system comprises of structural members, joints and connections, and each has to perform a specific role or a function. And a structural member may belong to one or more structural systems, and each and those may be serving different roles in each of the system. I'll just explain this point in the next slide that I'm going to show you. Okay, what this means, that how a structural member may perform or may belong to one or more different systems, and how it may serve different roles in each system. Let us see this. So I think this definition is quite clear. Structural system, what is meant by structural system? Now, how do we classify different structural systems? So as per design actions that are induced, we classify the structural system. Just to give you an example, if I say that it's a tie member, usually what does it indicate? Very common definition. What is a tie member? So I am saying, now, how do we classify the structure system? I am showing you as per design action, how do we classify? So if I say that this member is a tie member, what does it indicate? So generally it indicates that it is going to predominantly take tension forces. You understand? Hello. If I say that a particular member is, let's say, a strut, what does it indicate? If I say a particular member is a strut member or it's a strut, it indicates that majority or the dominant design action will be, let's say, compression. Okay. Or if I say that these members are put together in a truss system. So predominantly we understand that the design actions that the members of this system will take will be what? If I say that a particular member have been assembled in a truss-like system. So we understand that majority or the dominant action, as Mr. George and Mr. Jay are saying, will be axial forces, compression or tension. This does not mean that it will not take moments, but because of the geometry and because of the configuration, it will mostly be resisting compression or tension. Yeah. Or if I say that a particular member is a beam-like member, okay, or it's a girder, the first thing that comes to our mind is what? That if I'm, or it's a lintel, let's say, the first thing that comes to our mind is that the major design action or the dominant design action will be through flexure or bending and shear, correct? So we understand this intuitively. So we can, or let's say it's a footing element, and we understand that the loads from column, how those footings will transfer the loads from column to soil. So we say that if it's a footing, the dominant design action through which it will transfer the load from column to soil will be, let's say, through bearing action. You understand? So this is how, as per the design action, we may classify a particular structural system. Okay. Now, when we are picking members for structural system, there might be some members which we can call them as part of your area, or let's put it this way, that there will be some members or systems which will take the area load, or let's say we can call them as 2D elements. By 2D, I mean that they are having, of course, all of them have three dimensions, but if I'm writing it as 2D, I'm basically indicating that they take load from a certain area. Okay, so there might be some members or systems which have the purpose of taking area loads and transferring it to next set of members or systems. Then there can be some members or systems which will be mainly taking the line loads. So by line loads, I mean that they will be having a length and along the length, of course, they have the width and depth also, but the majority of load that they are taking is along the length of the member. So let's put it this way, that we will call it as a 1D elements because they are taking the loads along length. And then let's call them some elements as 2D elements. So for example, my slabs, okay, or domes or tensile structures or tensile roofs, all these I can put it under what? So all these I can put it under, let's say, members or systems which will take loads from area. You understand? Hello? Are you getting this point? Similarly, what can be examples of what can be examples of members or systems which take majority of their loads from a line? Line means in along the length, they are resisting the majority or taking the majority of loads along the length of their or along their longitudinal direction or along their length. So I can put, let's say, beams, okay, or what else? Trusses. So trusses have the purpose of taking the loads. Majority of the loads come on the trusses or beams along their length. What other examples come to your mind? So beams or trusses or closely spaced one direction beams are called as joists. Yeah. So these can be your different elements which are there to take the loads only along, let's say, one direction, or even my columns, because columns are also taking loads along one direction only. Majority of the loads are being taken along one direction. That is their axial direction. So I can come up with a classification like this as well. Okay. I can come up with another classification which is on the basis of the loads that they have to carry. So there can be, what are the major loads that we are talking about over here? So there will be a system for, as we call it, there is a system which takes care of the vertical loads. Now, all the vertical loads generally will act along the gravity direction, isn't it? So the system that we have in our structure to take gravity loads, usually gravity loads, are called as what? Gravity load resisting systems. Is that clear? Hello? Is it making sense? So it is usually called as a gravity load resisting system. And then any system that we introduce to take care of lateral loads are called as what? Now this lateral load may be due to uh, any possible loads, but majorly due to wind and earthquake, which as structural engineers we like to focus on. So a system for lateral loads, we will call it as the lateral load resisting system. Is that clear? So there can be this another classification for our structural system where we are classifying it based on the loads that it is taking. A system that we put for vertical loads, for taking vertical loads, which are majorly the gravity loads, we call it as the gravity load resisting system. And then a system for taking the lateral loads, which we call it as the lateral load resisting system. Then another type of classification we can do can be as per their orientation, right? So I like to call this as my horizontal system. Yes or no? I like to call this as my horizontal system, and I like to call these as my vertical system. Are you understanding this? Very basic discussion we are trying to have. So this can I can call it as my vertical system. Another classification we could have can be as per location. As per location means generally the system that we provide below ground in our in general terminology is called as what? The system that we provide below ground is called as what? So it is called as the superstructure, sorry, substructure. And the systems that are above the ground are called as superstructure. You all know this. So I can have a superstructure, and then can have another system that I will call as a substructure. So based on my location also, I can give this terminology superstructure or substructure. So this can be another way of classifying my structural system. So what is a structural system? As I told you, that structural system is an assembly of different elements, members, which have their purpose of taking taking loads, and they have to basically take care of the design actions that are generated due to the loads acting upon them. So if we try to construct a simple structural system, okay, let us come up with a simple structural system, a simple structural system in RCC, because I am talking, we are doing this course on RCC. So let us come up with a simple structural system for RCC buildings or reinforced concrete construction. So what can be a simple structural system in RCC? Yes, tell me. So first we have to come up with a 2D or a system which takes care of the area load. So let's say I have slab, okay. Then these slabs will transfer their loads to a one-dimensional element or one-dimensional system which are oriented along the length, and their main purpose is to carry loads along one direction. So I have, these are called as what? Beams. Hello? Yes or no? And then I introduce another system which also takes majority of the load along one direction, that is their length. So these are called as what? Columns. So this you can think of as the simplest type of structural system in RCC. So it's a slab beam column arrangement. Yeah. What is going to be the load path? So load path means how the loads are going to flow. So from slab to beam to column. Now all these are superstructure. That means these are all above ground. Now below ground, depending on of course your soil condition, we may have different structural system for the foundation or substructure. So from here, from the column, the load flows to substructure. And in this case, let's say we have an isolated footing. So what is your complete load path in this case then? So from slab to beam to column to isolated footing. Is this clear, please? I think very simple, very basic. So this was, let's say, there to take your gravity loads. So we had developed this system to take the gravity loads. Now suppose I had to take lateral loads. Suppose I had to take lateral loads. So how the lateral loads will flow? How the lateral loads will flow? So the lateral loads will also have the same load path. from slab to beams to columns to your substructure in this case, which was isolated footing. Is this clear? Hello. Now, generally, let me introduce another term. Generally, when your slabs or horizontal elements have to take lateral loads, because see, slabs are going to transfer their lateral loads to beams. So when my slabs have this purpose of also taking the lateral loads and transferring it to beams, we usually call the slabs as what in those cases? In those cases, we usually call the slabs as what? So usually those cases we call our slabs as diaphragms. So that action is called as a diaphragm action, through which the slabs transfer their loads to beams and then to columns. Is this term clear, diaphragms? Very easy. Okay. Now suppose I had a slab uh, and I did not want beams. So slab I have to have because I have to come up with a floor, but I did not want beams. So I could come up with which system? So I could come up with slabs and then columns and then to your substructure. So these types of systems are called as what? So where I try to eliminate the beams, those systems are called as flat slabs. Those systems are called as flat slabs or slab without beams. And then, of course, this substructure can be depending on the soil strata. So you might be having isolated or raft or whatever. That is a different discussion we will have. I am right now focusing more on the superstructure. So that will be called as a flat slab, where the load transfers directly from slab to columns. So gravity load can also transfer in this manner. Gravity load can also transfer in this manner. Lateral loads can also transfer in this manner. Now, when you have, let's say, a location where seismic loads are critical, or you have a high seismic zone region, you do not, for gravity loads, you can rely on the transfer from slab to column. But then for lateral loads, you are not very comfortable with the slab directly transferring loads to column because it's a potential weak zone over there. So what do we introduce in such cases? I'm just having a very general discussion. What do we introduce in such cases? So we introduce RCC structural walls, okay, or shear walls. Do you understand this? See, in this course, just one clarification. RCC structural walls is the technically appropriate term. This means a wall which is reinforced and which is able to take axial forces in plane and out of plane moments. So that is called as RCC structural walls. But the common name that we use for it is what? In the common conversation, the common word that is used for RCC structural walls is what? So it is shear walls, isn't it? Although shear walls take majority of their loads in flexure and axial forces, but still we call them as shear walls. So in this course also during discussion, if I'm saying uh, if I'm saying shear walls, it means RCC structural walls. Clear? Anyway, so in these systems where I am doing a flat slab, especially in high seismic zones, what happens that the load transfer between slab to column, direct load transfer, lateral load transfer between slab to column is a problem because it's a potential weak zone. So what do we introduce? What do we introduce in such cases? So we introduce RCC, structural walls or shear walls, and now the load transfer will be like this. Is this clear? Hello? Is it making sense, please? Yeah. So what was happening for my gravity loads? The gravity loads were flowing through slab to column. Of course, structural walls will also take gravity loads. Of course, the structural walls will also take the gravity loads. So my main gravity load resistance system was from slab to columns to footings or from slab to structural walls to footing. But I introduced another system for lateral load transfer and I called it as the uh, slab to structural wall to footing system, foundation system. Clear? So in one building itself now, I have come up with two systems, one for taking care of the gravity loads, the other for taking care of the lateral loads. And if you see, the structural walls are having to serve both purposes. They are there to take gravity loads also. They are there to take the lateral loads also. Are you getting this point? Yeah. Now suppose I had a very large span and I wanted to cover this span. Let's say I had a very large area and I had to cover this area. Uh, I did not want a lot of beams in between. It was a very large span and I wanted a column free, large, unobstructed area. So then what happens is, as you all know, that a beam slab system may not be the best solution in these cases for large spans. So then what do we come up with? So either we come up with domes, okay, or vaults or folded plates, isn't it? So in this case, what has happened? The system has changed. So we may come up with domes spanning in both directions or vaults or folded plates. So now the load transfer takes place from this elements or these elements which we have chosen to take area loads, and then it might transfer to some beams like things, and from there it might get transferred to your columns. Is it making sense? And same thing you can talk about in structural steel also. So in structural steel for small spans, we may have single members or girders. For large spans, we may come up with trusses. For taking loads from two dimensions or taking area loads, we may come up with space frames, or we may come up with composite uh, RCC concrete decks. So the systems may change in case of structural steel also. All right. Now another system that might be possible where you have large areas which you need to cover with small beams or not very deep beams. What do we do? Where you have to cover large column free spaces, we may come up with a grid slab or a waffle slab. Clear? So closely spaced beams, on top of it a slab, and then some primary beams at column locations. So the load transfer happens from your slabs to these closely spaced beams, to the main beams, to the columns. So you can think of these grid slabs or waffle slabs also. Any confusion till now? Now, how the substructural system changes? How the substructural system changes with the choice or with the changes in the condition of your underlying strata. So if you have a hard strata with good bearing capacity. Generally, you may come up with isolated footings. Yes or no? Okay. If your strata is, let's say, a weak strata, poor strata, and in your structure you have problems of uplift, maybe the isolated footings may not be a good choice. In such cases, you may have to come up with what? You may have to come up with what? So if it's a poor or a weak strata and there are chances of uplift, you may have to think about pile or pile raft, pile footings. Okay. If let's say you wanted to join, or if you wanted to have a common footings for multiple columns together, because let's say you wanted basements or there were certain other requirements, then you could come up with rafts, okay, or combined foundation systems. So the substructural requirement also depends on what type of strata you are getting, what type of loads you have to transfer. Depending on that, you may come up with different substructural systems also. Clear? So the important thing to understand is that first of all, which are going to be your members or elements that you are going to include in your structural system, how they are going to take the loads, and what is going to be their load path. So these are important things to understand. If I just asked you in this system that I had showed you, the slab beam column system, the slab takes the loads, and which are the major design actions in slabs, which are going to be the major design action in slab. So in slabs, the major design action that is developed will be what? Tell me. The major design actions that will be developed in slab will be it will be mainly what? So it will be a bending and shear, isn't it? Hello. So because of the orientation of the slab, because of the loads that were expected on it, uh, the design actions that are generated are majorly flexure and shear. In my beams, because of its orientation, because of its placement, because of its connectivity with slabs, which are the major loads that it has to resist? Sorry, which are the major design actions that it has to resist? So it is going to be flexure, hello, shear, torsion maybe. Axial, is it going to be a big problem? Although because of the portal action, axial forces do come in beams also, but usually they are not a major cause of concern for us. Understood? So beams have to mainly take flexure, shear, torsion. Now columns, because of their placement and because of their configuration, which are the major design actions that the columns have to take? Tell me. So the major design actions that column have to take will be axial, usually compression, and bending is possible. Biaxial bending is possible in columns, and to a certain extent, shear. Shear is not a very critical action, but shear also. Understood? And then when the load is transferred to your foundation system, depending on what type of foundation system it is, it has to resist certain design actions for that as well. Now, if my same slab beam column system had to take lateral loads, which would be the major design action generated in my slab, or now I am calling it as the diaphragm, let's say. So which is the major design action generated in my slab? It will be again be moments or flexure and shear, but this time I'll call it as the in-plane bending. or in-plane flexure. When it had to take gravity loads, this slab, it was out of plane flexure. Okay. But when it has to take the lateral loads, my slabs generate what are called as the in-plane movements or in-plane flexure and in-plane shears. Now, when this lateral load gets transferred to the beams also have to resist again flexure and shear. And when it goes to columns, columns again have to resist axial, bending, biaxial, bending, and shear also becomes important. Is it making sense? Tell me. Yes. Similarly, if I had this slab beam, slab column shear wall system. If I had this slab column shear wall system for gravity loads, my slabs will have to generate or I will develop flexion and shear. Columns will develop axial forces, biaxial bendings and shear. My RCC structural walls will develop out of plane movements, in plane movements, and axial forces. And same for lateral loads also. To resist the lateral loads, my slabs will have to resist the in plane movements and in plane shears. Structural walls will have to resist the out of plane and in plane movements and axial forces and shears, and then isolated footings. Suppose I had a dome like structure. What are the predominant actions in this type of structural system or this type of arrangement? What are the dominant actions? So in this case, flexure does not remain a dominant action because of the configuration that we come up with. So dominant actions may become your compression arch forces. Okay, is it clear? Is it clear, please? Yes, you know all these things. So the compression forces, the radial forces, the meridional forces, uh, these may become important in structures like domes or walls, etc. All right. Major design actions in grid slabs, offal slabs, they are also again flexure and shear, talking about the slabs. So, so these were a few things that I just wanted you to understand related to structural systems. Now, just to make one more point, that how does the choice of material affect the system that we are going to pick? Tell me. How does the choice of material, building material affect the choice of structural system? Yes, please. Tell me. So let's say you know all these things, but if I had, let's say, masonry units only, okay. So if I only had masonry, masonry means where from clay you come up with units, masonry units like bricks or similar masonry units, or you have a stone. So if my material is only restricted to masonry units or stone, then I would like to have systems which predominantly take loads in which action? Tell me. If the only choice available with me is, let's say, masonry units or stone, which structural systems I may have to select? So the structural systems, as Mr. Zoeb is saying, I will have to come up with structural systems that are suitable only to take the design actions of compression. Okay. So only compression will be a suitable design action which my masonry system can resist, or a stone system can resist, or a system made out of stone can resist. My compression will be the only major design action. To a certain extent, bending and shear, but those resistance that my masonry units or stone can offer to bending and shear are very minimal. Tension is another action which my masonry or stone or systems made out of masonry or stone cannot resist. Tension, flexure and shear. These three actions, a very small value it can resist. The major it can resist is compression. So because of the choice of material, how my structural system shape gets affected, that if I have to cover a long span and I only have a stone or masonry units available with me, I have to do what? I have to come up with a dome. Are you getting it? Or an arch. Hello. I know it's very basic, but I hope you are getting sense of it. Yeah. So I have to come up with a system like this because of the material I had that can transfer the loads in the dominant action. Correct? Are you with me so far? Or suppose I had a system which was, let's say, structural steel. So therefore, in old constructions, in old temples, in old forts, in old buildings that you visit, which are made in stone or masonry, what do you find? You find a lot of arches. You find closely spaced columns. So if it has to be, if you cannot come up with a arch, what do? You provide very closely spaced columns so that the beams that you have, the beams that you put on top of them, the stone beams or masonry beams that you put on top of them, they develop very small bending and shear because of closely spaced columns, and then the load can be easily transferred. So either you see closely spaced columns with deeper beams in stone construction, or you see the use of arches. Okay. So all those things are because your structural system is comprised out of material which can only take a particular design action very well. Similarly, if you are seeing construction in structural steel, which actions can structural steel take very well? So it can take tension very well. Hello. Yeah. Structural steel can take tension very well. It can take compression also, but compression is limited by the slenderness. So the problems related to slenderness or buckling affect the compression capacity, but it can take tension very well. So therefore, when you are seeing structural steel, what happens is that the type of and bending and shear, uh, again, it can take obviously, but the flexural bending, sorry, I should say the bending compression again becomes a problem. So therefore, in structural steel, what do you see? You see a lot of systems which are comprising of trusses. So in trusses, what do we do? That all forces are converted into axial, and those members which are under compression, there we provide uh, elements in such a way that their compression values are reduced, or their compression stresses are reduced. So you see a lot of trusses or girders with secondary or lateral supports or systems like those in structural steel construction. Now in RCC, what happens? In RCC, what happens? That which action is RCC suitable for? So in RCC, we do a good thing that for compression we have the concrete, okay, and then for taking tension, because the cement concrete is inherently poor in taking tensions. To take tensions, what do? We reinforce with we reinforce the concrete with bars, isn't it? So when we do a system, when we use material like RCC, what have we effectively done? That we have integrated two now different materials together. One is to take care of the compression through concrete, and then we have a material which is the reinforcement to take care of the tension. So basically, we have combined best of both the worlds. Reinforcement is there to take the tension, and concrete is there to take the compression, isn't it? So when this use of RCC started, let's say 150, 100 years ago, a lot of different other structural systems evolved, because now you had a material which was good in taking compression also, and which was good in taking tension also. And RCC was a material which you could mold in whatever shape you wanted as well. So it is very difficult to mold. It is very difficult to mold stone in different shapes, or it is very difficult to mold steel in different shapes. But it is very easy to mold concrete in different shapes. So when the use of reinforced cement concrete started, you could basically come up with any geometry, any shape, and you could always reinforce it with steel, and then uh, you could get good resistance in compression also and good resistance in tension also. Is that making sense? Now, uh, one very big problem with RCC is what? So because we have integrated reinforcement and concrete together, one very big problem is of durability. You understand? So why durability becomes a very big problem? Because reinforcements are subjected or are prone to rusting. And once your reinforcement rusting starts, it will create problems, because it will create problems because number one, your reinforcement rusting will lead to volumetric changes. So it will lead to crackings. Once your concrete starts cracking, it comes into contact with the atmosphere, and then it further deteriorates. So there is a big problem of durability in your concrete. Typically, if you see even 50 to 60-year-old concrete structures start looking so poor, isn't it? Hello. I mean, 50 years is their design life, we say. So even a RCC structure after 30 years start looking so horrible. Yes or no? Whereas if you were to see, let's say, a construction done in masonry or stone, even after 300, 400, 500, 1000 years, it does not deteriorate so much, right? So when we use stone or masonry construction, the durability is very high. It has a very high, very long life period, lifetime. But in RCC, durability is a very big issue, because we have combined or integrated both these items together. So the rusting of reinforcement and the corrosion leads to a very small design life for RCC. So one of the biggest problems in RCC is its durability. Understood? Okay. So these were some thoughts I had on these structural systems. Now just going back. So we're discussing the different types of structural systems. So in this course, when we are going to discuss what are the different 2D area members or elements that we are going to discuss. So we are going to discuss the slabs, obviously. We are going to discuss the flat slabs also. Okay. The major 1D element of which takes loads from the along their lengths will be focusing more on beams only and deep beams also. The members for taking vertical loads will be focusing more on the design of columns and structural walls. And for our substructure, we'll be talking about the isolated different types of substructure that we will be discussing, isolated or combined or raft or pile caps. So these are the, let's say, members or elements that we'll be covering during this course. Okay. And of course, we will also be discussing the diaphragms, which are nothing but your slabs that take the lateral loads uh, in the in-plane movements and in-plane shears. So we'll be discussing all these things. Okay. And as I was telling you, for any structural system, it is very important that you understand the load path. So the load path will generally be from a horizontal system to a vertical system and onwards to the ground, or what we can simply call it as from superstructure to my substructure. Clear? So in a good structural system, it should always have what? Multiple load paths. Do you understand? What is the meaning of this? Should have multiple load paths. What does this mean? This means that, let's say, very simple example, if this was a cantilever, okay, I had taken this cantilever from a column. I am showing you the elevational view. So let's say I had this cantilever beam coming out from a column. Now suppose there was to happen a failure at this junction in moments. So suddenly, let's say the reinforcement slipped or there was some failure at this cross section, then will this cantilever beam remain stable or will it remain in equilibrium? Tell me. Hello. So answer is no. If there was to happen some failure at this junction between the beam and column, this cantilever beam would just fall down, isn't it? It would no longer remain stable. Is this making sense? So this system only had one load path. So from cantilever beam to this connection to the column, this cantilever beam system only had one load path. But let's talk about two columns and I have put a beam on top of it. Now even if at this junction there was some failure or some happening, still it had a support over here. Understood? So I could say that there are two load paths that exist. Actually, it's a one load path only, but I could say that there are two load paths that exist. Understood? And it was integrally connected. Here I am talking about a portal system, let's say, where beams and columns are integrally connected. So this system had multiple load paths available. Are you with me? So in a structural system, we always wish to have a structural system having multiple load paths. Or for the same example, if I had a flat slab system with columns with a slab connected directly to columns. Now, what is the problem with this system? That if there is a lateral load, if there is a lateral load, and if there is a failure at slab to column junction, or even under gravity loads, but more so under lateral loads, if there is a failure at slab column junction, it will lead to a catastrophic failure, direct failure. So this does not have multiple load paths, let's say. But if I introduce RCC structural walls over here. Then structural walls can take care of the lateral loads. Of course, some lateral loads will flow through the slab column junction also. So there is a availability of multiple load paths that we have. So whenever you are doing a system, you should always try to have a system which has multiple load paths. It must have a well-defined load path, and each element along the load path should be properly designed and detailed for the expected design actions on them. Is it clear? Yes, no? Okay. So because I use the term design, what exactly would we mean in RCC if I use this term design? What exactly are we going to mean by it? Tell me. What are we exactly going to mean by it when I use this term design? So, in the context of RCC, when I use the word design, I would be mainly, I would indicate, or it would mainly mean that by design, I would mean that I'm going to finalize the sizes and orientation of each member that is in your system. Okay. So by design, I would mean that my first uh, objective or goal would be to finalize the sizes and the orientation and the placement of the members. That would be my first objective. My second objective would be to find out the reinforcement. Uh, so by finding out reinforcement, I would say to find out the diameter and number. So which bar dia and in how many numbers, or at what spacing we are going to place and where we are going to place. So that would be important. And then the reinforcement layout, how it would be placed. So first the reinforcement quantity and then how to place it. And of course, before that, finalization of sizes and orientation. So when I say that I have to finalize or I have to do RCC design, I would basically mean that these would be my objectives. Clear? So throughout the course, this is what we are going to attempt at doing. Any confusion? Okay. So let us, till now we were just discussing what is meant by structural system and what is meant by design and just general discussions about a structural system. So now let us see that how the design codes has evolved over the past almost 110 years, 115 years. And as you all know, which code are we talking about? So we are throughout this course, we are going to talk about the ACI code. Let me just show you the ACI code. So we are going to talk about the ACI 318 and the current revision or the current version is the ACI 318.25 right now. So this is the code that we are going to be discussing. Let me just show you the code first. I don't know, what are you able to see right now? Is this code visible? Blank. The code is visible? Yeah. So this is going to be my ACI standard. It is the ACI 318. Why? What is the significance for this 318? So 318 is the committee number. Okay. Simply, it's the committee number. So it is the 318th committee which sat together, and the members of this committee number 318 came up with this building code for structural concrete. So same way we have the IS 456. So the 456th committee sat together and came up with this code. Or we have the IS 800. So 800th committee sat together and came up with this code. So this number does not have a lot of meaning. Or we have the AISC 360. So the 360th committee sat together. Or we have the AISC 341. Okay, or we have the AISC 358. So these numbers don't have any meaning. It just indicates the committee number which was constituted to look into these particular aspects. So this is the building code for structural concrete, and it includes the code requirements and also the commentary. So one good feature of these American standards is that the commentary is published with the code. Unfortunately, in the IS, they don't publish the commentary. If you see the IS 456, I think the last time a commentary was published to 456 was for the 1978 version. I think after 1978, the code was not revised, isn't it? I think after 1978, the first time it was revised was in 2000. Am I correct? Hello, tell me. This 2000 is the current version. So 25 years ago, the version was revised. But before 2000, I think the version was 78. Yeah. You didn't have any version in between. So last time commentary was published was for IS 456 1978, and I think that was published in 1980, and it is the SP24, I guess, if I remember it correctly in the Indian context. It is the SP24, which is a code commentary to IS 456 1978. So 22 years between the 78 and 2000, and the current draft that is out. Maybe in 2026 we might get a revised 456, who knows? So it will be what, 26 years. So actually that is a very, very long time that the Indian committees take to revise standards. Same as the story with the IS 800 also. So IS 800 was in 1984. Then you didn't have any revision, and then you got the revision in 2007, isn't it? So 23 years again. So somehow the Indian Standards Committee takes a very long time in revisions. Anyway, and then they don't come up with commentaries also. So the good thing is that the ACI committee, ACI codes or the AIC standards also always come with the commentary. So commentary and code are together published. So this is the ACI 318. This 25 refers to the year in which it was revised, or the current, the version, let's say. So 25 will indicate that this was revised in the year 2025. So before 2025, the version that was there was what, which was the version of 318 before 25. So it was the 19 version. Okay. And then we have the units mentioned over here. So this code is in the SI units, Standard International Units. In US, they mainly follow the FPS system or the imperial system, the foot pound system. So you will always get two versions of the ACI codes or the AIC standards also. So one will be in the metric system or the SI system, and one will be in the imperial system or the FPS system. Understood? So this is the code in the metric system. So throughout the course, we will be doing the calculations, or we will be referring to the metric units code. I won't be going into FPS system. All right. How many of you do or are required to do projects in FPS system? Anyone who is doing their projects in FPS, following the FPS systems? Foot, pound, inch system, anyone? No one. Okay. So yeah, we will be referring to the ACI 318 and we will be referring to the metric system or the SI system of units throughout the course. So this is the code, and this was published for the first time, or it has almost 110 years long history. So if you see, I don't know if you're able to see this. I've just zoomed in. So the ACI code was approved by the ACI standards for publication, and it was first published in 1908 and revised in the subsequent years 1910, 20, 27, so on. Is it clear? I think there is a misprint over here. It should not be 156, it should be 1956. So just make this correction. It cannot be 156 over here. This has to be 1956. So these are the different years in which the ACI code was published. So it has a very long history. The first credible code, I would say, was published in 1910, and from 1910 to 2025, almost 115 years long history of the 318. So what we will do is that tomorrow we will just have a quick look at the historical development of this code throughout the past century. Okay, and we will have a quick look at the historical development, and then we will go back to the ACI 318 2025, that is. So this is how we will be going ahead in the next session, that is in the next session tomorrow. Now what we will do after this session is completed, uh, the recorded session will be uploaded within the next 2 to 3 hours. So those who want to watch it again, or let's say they could not watch the live session, they would be able to watch the recorded session on the portal. Okay, so that will be available by afternoon. So I think that's all for this session then. When we meet in the next session now, we will start with the historical development of ACI code, and then we will have a look at the ACI 31825, how it is laid out, and then we will begin with the chapters 1, 2, 3, and 4. So that is going to be the plan for next session. So that's all for this session then. Thank you very much, and bye bye. Bye bye.